This is part 11 in a series of videos in which I am repairing and restoring a number of Intel MDS units. In the previous videos I've got as far as testing the main processor board for one of the units, that's this board, and also showing the test jig I made for doing this. Now, of course, there are many ways you could go about testing faulty units, and the information I'm giving in this series of videos is not really meant to just show how to repair an MDS unit. What I'm trying to do is show various methods and techniques for fault finding and restoring equipment in general. So while we're going through this, I will have to focus at some points on the particular MDS units that I'm repairing, but just bear in mind that all these techniques are really aimed at any type of restoration of electronic equipment. So the approach you take is entirely up to you. You could of course just assemble the entire unit, plug all the boards together, plug the power supply in, switch it on and hope for the best. I very rarely take that approach. I tend to be a bit more reserved in the way I approach these restorations. If it's just a simple repair, then yes, you could do that, and if you know the unit's been powered up already, then again that's one method you could use. But I tend to go through more of what would be a production process, where each individual assembly is tested, assessed, repaired as necessary before it's put into the final unit. That way what I can avoid doing is damaging other boards if there's a fault on one of the boards I'm working on. For example, if there was a dead short on this board, I don't want to plug it into the in-out board. But as ever, the approach you take is entirely up to you, and it's meant to be part of the fun of the process. Is be inventive, do it the way that you want to do it. If it doesn't work, try something else. Also, when you build test jigs like this, then all the testing I showed for the test jig, I of course don't need to repeat again in the future. I've now got the test jig, it's been tested, I know the wiring's correct. So all I have to do to test the next processor board is unplug this one and plug the next one in. And as long as it's the same type of board, then I can just go ahead and start the testing. Also, I still have the analyzer probes set up on the clips, so I can clip that onto the next board, and the process can be repeated as many times as I have boards. So although it initially seems a slow way of going about this process, ultimately if you have more than one unit, it's a very quick and efficient way of carrying out this testing. It's also very thorough. What I did off camera from the previous video is go through the various parts of the system. I trapped the logic analyzer on the various parts of the boot up sequence for testing various parts of the system. There is a diagnostic part of the boot up. I went through all that, and the board seems to be behaving fine, at least as a standalone board. There were a couple of things I found with it. It did have a tendency to crash if I flexed it. And that just turned out to be a flaky connection on one of the sockets. I cleaned it up and now it seems to be fine. Other than that, it seems to be working 100%. And that is a good example of why this is a good technique to use, or at least in my opinion. That's the sort of fault that could drive you insane if this was plugged into a finished complete unit. Random crashes of systems like MDS's are very difficult to track down because of the nature of the way they work. Okay, so that's the approach I'm taking, but as I say, just bear in mind that this approach can be applied to any piece of equipment you're working on, and it's not specific to the MDS units, but I will have to focus on the MDS unit details in some videos. So now that I have this board tested, the question is how to proceed. What do I move on to next? And really what the sensible next step would be, if you didn't want to go to the trouble of making any more test jigs, is just to plug this into a chassis, connect this cable to the in-out board, and then start trying to power it up and see if it works. The problem is with a system like the MDS is knowing when it's actually working. Although it might appear to boot and you might get something appear on the screen, there are so many in-out channels and so many other aspects of the system that you can't just carry out a single test and assume it's working. So we have two real in-out routes for data from this processor board, we have the in-out channel, and then we have the backplane to which we connect boards like floppy drive controllers, expansion memory, that sort of thing. We've got the parallel interface as well, so we have the in-out, and then there's another interface as well. So depending on the direction you want to take your own testing, it's entirely up to you. But I do like to get to the point where we can get something on the screen. Now, these boards do have built-in diagnostics. The listing I showed you does include diagnostic sections of code. In fact, I mentioned that the ROM on this board is split into two major blocks. One is for the boot monitor and the other one is for diagnostics. The problem with diagnostics, built-in diagnostics, I've always found is that if they run, you don't need them, and when you need them, they won't run. That's not always true, but it's a general rule, and I tend to prefer to at least get the fundamental aspects of the board working before I try to connect everything together and run any built-in diagnostics. That said, I think the next thing to do would be to work towards getting something on the display of the MDS. So what this board plugs into to drive the display is the in-out board. So this cable will connect to the in-out board. So I'll grab an in-out board, we'll have a quick look at it, and I'll explain why that's not the approach I'm going to take. So this is the rear panel assembly for an MDS unit. We can see we have the in-out channels down the center, room for some further in-out expansion, keyboard connector, brightness and contrast control, and it's a fairly significant assembly in its own right, but what I'll do is take the steel plate off. I've taken the screws out already and we can see the board underneath. I've mentioned previously that the MDS units are a collection of three major assemblies, each one with its own microprocessor, and this is the second one of those. You can see it's got its own set of ROMs, its own processor, and this is kind of a slave processor to the main processor we've already looked at. So the main processor will send commands to this board, and this board will carry out the commands as instructed, and it does that in kind of an autonomous way. It's not constantly overseen by the central processor. The central processor is always in control, but once a command has been issued, this board will tend to be able to complete the command without further assistance from the central processor. There are some areas where that's not always true, but fundamentally that's the way the system operates. We've got an 8080 processor on this board. As I say, we've got the ROMs, sounder and various other support chips, and part of the circuitry on this board is the CRT driver, so the monitor driver circuits and character generator. So the big grey cable we saw from the central processor unit plugs in at the top here, and then the commands that are issued from the central processor unit are used to govern what goes on here. But there are also some live signals, kind of live signals where information that's meant to be fed through to the monitor come into the monitor buffer within this board, and that's what I want to look at next. So rather than just plugging all this together and hoping it all works, which it may well do, if it doesn't work, then obviously the problem you have is, well, there's a fault on this board, there's a fault on the main processor. If there is a fault on here, you could end up damaging the main processor. So what I like to do is, as much as possible, eliminate the possibility for chasing myself in circles trying to track down a fault that may not exist. So for example, let's say we plug all this together and nothing appears on the display. Where are we going to look to see where the problem lies? So the monitor connects onto this connector on the center, and so what we'll do, rather than jumping straight in and connecting the entire thing together, we'll test the monitor first on its own and we'll see if that works. At least that way we can be certain that if we plug all this together and nothing appears on the monitor, then at least we know it's not because the monitor itself is faulty. and that at least gives us a starting point to fault find on this board. And then once we've got that part of it working, we can start looking at the rest of the in-out channels. And a lot of them are fairly independent, so we can test a lot of this as completely separate units. As long as the processor's running, then we can treat the in-out channels as almost separate entities. And of course, looking at the processor running will be very much like treating this as a separate board, where we're looking to see if this processor system can run on its own, and then we can start looking at how it's responding to commands. So the next step is I'll get the monitor on the bench and we'll make up a test jig so we can run it independent of the MDS boards, and once we're happy the monitor's working, we'll actually try plugging the whole thing together in the next video and see if we get anything out of this at all. So this is the monitor assembly out of the MDS. You can see it's very simple, very standard type of monitor, CRT monitor. Simple interface, just 10 pins, and the interface to the monitor is very typical of monitors of the time. In fact, it's pretty much so standardized we will probably end up using an LCD monitor for some of the testing. But what I want to do in this video is make up a test jig so that we can test these monitors. I'll then give this particular one a really good clean, and we'll refit it to the chassis that we started to assemble in an earlier video. And the goal is to assemble that chassis up to the point where it's running. We can then carry out further diagnostic testing, and if necessary write some specific test procedures before we really start to look at the faulty boards, so at least we have a way of fully testing them and doing some proper diagnostics. And also we can fully assess the built-in diagnostics, make sure the version of the firmware we've got is what we think it is, and then go from there. Okay, so what we've got is obviously the CRT. If you do take these out, be very careful. The neck is very fragile. If you break that, then of course you'll destroy the tube, but also it can be quite dangerous. Also, the tube itself is effectively a huge capacitor, and it can have thousands of volts on it, and it can retain that charge for a very long time. So be careful when you're working around the high voltage cap and the EHT transformer. If you don't know what you're doing, I advise not to open this up, but if you do open it up, then be really careful. Step one, which I've already done, is discharge the tube. So the way I do that is I clip a grounded lead onto the chassis, and then making sure you get a fairly good quality lead that will withstand the high voltage, you clip a insulated screwdriver onto the other end, gently put it underneath the cap, and at some point if it is charged you'll hear a crack as it discharges. Don't do it once, do that several times, but unless you really need to, don't take this cap off. There's very rarely a need to do that unless you are replacing the transformer or the tube. If you're taking the board out, just unplug the board at the connector down here and leave the rest connected up. I will be giving this tube a really good clean on the assumption that it works. Also, I'm not quite sure what it is. There's a lot of kind of sticky goo around the EHT cap. Not something I've seen before, but it's either something they put on to seal it, or it's the cap itself starting to degrade. Either way, I need to clean that off because it will attract a lot of dust and debris, and at some point it will start to cause some arcing. So, very simple test jig. All it's comprising of is an edge connector. So these are 3.96mm edge connectors. I've cut one to length, so it's 10 way, so it will fit onto the edge connector. I've looked at the schematic for the CRT, and the lines we have, there are two ground lines, both need to be connected. We've got a pot for the brightness control. We've got plus 15 volt supply, a plus 15 volt return, which I haven't connected. That's just for regulation purposes. It's not needed for the test jig. And then we've got a vertical drive, that's a vertical sync pulse, horizontal sync pulse, and then the video. I'm going to drive the three active signals from some signal generators just so I can fully test the CRT and make sure it's working right across its intended range. So this test jig just simply plugs into the CRT connector, so it will just plug into this connector, and that's it. All the grounds from the signal generators are connected together, and then one of each goes through to the 3 active signals on the monitor. So I'll just get this turned around so we can see the screen. Okay, I've got the monitor connected to the test jig. I've got 3 signal generators connected to the 3 active signals, one for vertical sync, one for horizontal sync, and one for the video. They're not synchronized, so I won't be able to lock anything on the tube, but then I want to be able to just create images of a sort on the tube, so I can check the performance of the tube, the performance of the drive circuit, and the bandwidth of the monitor as a whole. So I'll explain what I mean by that shortly. Hopefully you can still see this. I've dimmed the lights in here so that hopefully the image on the monitor will be clearer. I've got the brightness pot set to central point. I've got the power supply set to 15 volts at 1 amp, which should be about the specification for this particular monitor. Should draw about somewhere between 12 and 15 watts, and so current limiting to 1 amps should hopefully save it if there's a short on the board or some other issue. Okay, so I'll turn the power supply on. So it's drawing about 350 milliamps, and there are obviously no active signals going into it yet, so it won't really do much. I'll now turn on the 2 signal generators driving the 2 sync pulses, so that's horizontal and vertical. And we should now get a raster of kinds if I've got this hooked up right. I'll try turning the brightness up. There we go. You might be seeing some flickering on the video, but that's because of the refresh rate of my camera. It's not visible on the actual monitor. But as you can see, the monitor's working. The width of the raster is about correct. The way they're adjusted on these MDSs is this will be adjusted to give you the width of text that you'd normally see on the screen. And what I'll do now is I'll turn on the video modulation signal, so we should be able to start producing some patterns, some vertical patterns on the display. So as we can see, we're getting some vertical bars, which is what it should be. And also, if you notice, the edge of the bars are quite nicely defined, as is the dark section between the 2 bars. What I'll do now is increase the frequency of this signal, and what we should see is 2 sets of bars. Now again, these aren't synchronized with each other, so you'll get these weird artifacts moving across the screen, but we can ignore those. So I'll just change the frequency, and now we're getting 2 sets of bars. I'll just try and slow them down a little bit. So as we can see, we're getting quite good performance. I'll just turn the brightness down a little bit, so that's more in line with what we would be seeing on the MDS itself. And again, ignore the flickering top to bottom. That's just caused by the frame rate of the camera. But as you can see, we're getting very good performance on this particular monitor. I'll try going higher again with the video signal, see if it can still keep up. Again, I'll try to lock that a bit better. It won't lock completely, but it should slow down. And again, very good bandwidth, good separation between the dark and light sections. So it looks like this monitor is working fine. Height's what it should be. And again, what you can do here if you want to is use this test jig to set up the initial height and width for the monitor, and also the dark level clamp and brightness. So if I switch the incoming video signal to a ramp rather than this pulse that we're getting here, then we should be able to see the grayscale on the screen. So I'll just change that. Let's change the frequency first, so we're getting one sweep per frame. And now I'll change the signal to a ramp. Try and synchronize it a bit better. And so what we're seeing now is the grayscale on the screen. I'll turn the brightness up and we can see there are 3 grayscale bars plus the background, which is what we should be getting. So it's 4-level grayscale on here. And so we can see that's all working fine. We're going from full bright. It's slightly out of focus, so I'll need to change the focus very slightly, but other than that it's a very nice sharp picture. And again, this means that we know now that the monitor works, we know the video input to the monitor works, and we can now connect this with a high degree of confidence that if we don't see something on the screen when we connect it to the in-out card, that the fault does not lie with the monitor. And this means that the monitor is now part of a reasonable test setup, because we know it works. And that's kind of what I'm aiming for with this approach, and it's why I use this approach. It means that anything I bolt onto the chassis, we can have a fairly high degree of confidence that it's actually going to be functional. And that means that by the time we start bolting more parts onto the chassis, then we're not going to be chasing faults in many different areas. It's just going to be hopefully the last thing that we plug in is the thing we need to be fault finding on. And so we can use the chassis itself as a good fault finding tool. Okay, so next step is to get this bolted back into the chassis. That's the chassis I started to assemble previously, and one of the things I need to put in place before I can bolt the monitor in is actually the floppy drive bay, but we'll look at that now on the chassis. Let's get the chassis back onto the bench. So this is the chassis that I showed in a previous video. As you can see, I've already started to assemble this. I've got the backplane, power supply bracket and cooling fan in place. This has all been thoroughly cleaned. I've repaired any damage to the plastic moulding. So the next step before I can install the monitor is to install the platform that the monitor and the floppy drive sits on. So again, I've given this a very good cleaned it on both sides, and whenever I clean these, incidentally, I do try to make sure I don't remove any of the original writing. I think that's of historic importance or interest to these units. I always try to retain that. So this particular mounting bracket sits in this position. It's held in place with 5 screws, so I'll just get those screws put in place now. I won't show that on camera, but there's 2 screws at the front here, 1 at the back and 2 on the other side. So I'll get those put in and get the camera back on. Okay, so this is firmly bolted in place. Now before I can fit the monitor, I actually have to fit the floppy drive mounting bay first, because the screws sit in front of the monitor faceplate, and if I try and fit the monitor first, then I won't be able to get to these screws properly. So I'll put that in place first. I will have to drop the floppy drive into it just to make sure that it's properly aligned with the opening in the front of the moulding. So I'll just grab the bay for the floppy drive, okay, which is this, and it sits in this position. 3 screws that hold it in place. But as I say, to get this properly aligned, there are some slots on these screws. Now, in theory, it should be very close just by letting the recessed bosses sit in the moulding. But it's always worthwhile at this point making sure it lines up, because if it doesn't, you've got to take the monitor out again. So I'll get these screws put in, I'll get the 2 screws at the back put in, and then I'll slide the floppy drive into place and make sure it all lines up. So I've got the bay for the floppy drive bolted into place. I put 2 of the lower screws in, I'll put the 3rd one in later once it's all aligned. I've left the 2 screws on the back side loose, so I can move this back and forth to adjust the position of the bay relative to the case. What I'll do now is slide in place one of these miniature floppy drives. if ever you find you can't repair one of these, you could always fit wheels to it and use it as a go-kart. But let's get this slid in. And the idea is there's a recess moulded into the front of the case, and the front plate of the floppy drive should be a good fit in the centre of that recess. So slide it forward, and all being well, it will pop into place. There we go. And what we can now do is turn the chassis round and look at the front, screw the floppy drive to the bay to make sure it's in the right place, and then what we can do is tighten the two screws on the back side of the bay to make sure that when we take the drive back out, this isn't going to move. So I'll do that now, and then I'll pop the drive back out and we can look at mounting the monitor in place. Okay, that's the drive bay fitted and aligned. Obviously the drive needs cleaning, and I haven't got round to that yet. But what you're looking for when you install this is that the height is correct. There's actually quite a small clearance with the operating lever on the drive. You've got about 0.5 millimetre top and bottom, so you do need to get it accurately aligned. And also the line alignment down the left hand side, the bolt holes on the bay bracket are slotted top and bottom, and the idea is it allows you to align the bay so that the edge of the drive, when it's bolted into the bay, is obviously lined up with the side of the monitor bezel, otherwise it'll look really bad. So carefully align that, tighten the screws on the back, and then we can take the drive back out to lighten the chassis, but it won't allow the drive bay to move because that's now bolted into position. And you can tell if it's right because firstly it will be aligned down the side, and also the lever will move freely and it won't bind top or bottom. If it's binding top or bottom, then it's not adjusted correctly, and you need to readjust it and try again. So that's done. I'll take the drive back out and then I'll spin the chassis around and we can refit the monitor. Okay, we're ready to refit the monitor. So the first thing that goes in is the bottom part of the monitor screening can. So I've given this a good clean as well. Now of course you could get this re-coated, replated if you wanted to. I tend not to do that unless the owner specifically wants it. I prefer to retain the character of the unit along with any historical relevant information, signatures, serial numbers, version numbers, that sort of thing. So the first thing, as I say, is to align this. It doesn't go all the way to the front. It aligns with some slots on the bottoms and bolt holes, and then the monitor sits inside of this, obviously facing forwards. So I'll grab the monitor chassis, and that then goes inside this particular chassis. Now I'm going to have to move the camera out of the way to do this because the tripod's in the way and I don't want to hit the neck of the tube on the tripod while I'm doing this. So I'll just quickly pop the monitor into this cage and then I'll get the camera back on. So I've got the monitor sitting back inside its screening can. Next step is to loosely fit the 4 mounting screws, and then we can align the monitor with the front of the case and tighten the screws down. So I'll get these screws loosely fitted to start with. Okay, they're loosely fitted. What I'll do now is spin the chassis around so we can see the alignment of the tube relative to the case. I'll adjust that and then tighten down the screws. So we push the monitor assembly as far forward as it will go until the tube is making the best contact we can get it to make with the surrounding bezel. It might need centering, moving left or right, rotating, and then we push it all the way forward and tighten the screws down. And as I say, we're aiming for the smallest gap we can get between the tube and the bezel. So once I've done that, I'll spin the chassis back round and we can fit the outer part of the screening can. Okay, so the monitor's aligned with the chassis. I've tightened down the 4 mounting screws. Final check to make sure everything's secure and clean. There's nothing protruding, nothing loose in there. and what I can do now is fit the outer part of the shield. So again, this could be replated if you want. I've cleaned it. There is obviously some underlying corrosion, and that's not something I'm going to address here. If the owners want me to, this can be dealt with, but it's not going to cause any problems. It's very minor surface corrosion, and it's to be expected on something this old. You could get it replated, but I don't want to remove the stickers or really interfere with the way it looks. I think it's just part of the character of the unit, considering its age. So this just sits down. There's a couple of slots at the bottom it goes into, pushes all the way down, and then it simply aligns with the holes in the shield. So it's just 6 screws that hold that in place. Okay, that's refitted. So what I've been doing is I've been refitting the screws. They're in slots. I've just been making sure that the side panels of the screen can all line up with the top edges of the outer part to make it all look neat and tidy. So that's that part done. The next thing, I'll flip it around and we'll reconnect the test jig and make sure that the monitor still works. Okay, so as we can see, the monitor still works. We've got now the basis for a working chassis. We can start plugging the various parts in. So that's it for this video. In the next video I'll look at plugging in the in-out card. We'll connect the processor board that we've tested so far, and we'll see if anything appears on the screen. If it does, we'll start doing some in-depth testing on the in-out card, and if it doesn't, then of course we'll start doing some fault finding.